Hey everyone, welcome to my video on the center of mass with 2D laminas. And just to reiterate what we saw in the last video, laminas are looking at these shapes that have constant density like plastic or acrylic, things like that, where you're not going to get really any piece that's heavier than any other piece in this entire shape that's right here. So we're just assuming constant density over this whole thing for these problems. And what I want to do is find the center of mass of a region bounded by two curves, assuming constant density over that whole region. So what we can try is something similar to what we saw in the last video, which is taking rectangles, and I'm going to draw in a couple extra here. So let's say I got a rectangle here, and you'll have to pardon my drawing skills on this. Maybe another rectangle right here coming down. So they should be kind of the same width going through there. But I got a couple rectangles, just looking at those guys going down right there. And what we want to do is the same thing we did before, calculate the moments on a lot of these rectangles and just use this as like a big composite of rectangles that I'm adding up. So we did that in the last video, which is looking at, if I have a bunch of rectangles together, how can I find the center of mass of that shape? And you get all kinds of crazy shapes, but this one we're using really skinny rectangles to make these kind of curved shapes, and then we'll think about taking a limit as these rectangles get smaller and smaller. So think of, say, some center of mass that's, located somewhere right in the middle of all these guys. And what I'm going to do is sort of complete this chart down here to add up some of these. So we need to come up with something just for the rectangles. So we'll look at what is the area and the moments of just one particular rectangle, and then we'll look at adding those up. So a local x bar, y bar. So we need to come up with a name for where is this particular rectangle going to be that's right here. And if you think about it, how far over am I going to go? So this is from the x-axis. So how far over is this guy right here? And you might say, well, I don't know, we're going over a distance x from here, and that would be a good enough name, right? So we're going over a distance x right there. For any particular rectangle Ri, you might say that's maybe xi. So you get like a x1, x2, x3 that you're adding up that are all sort of different coordinates in that shape from each of those rectangles. What is the y coordinate? Now this one, I'm going to go a little bit further than just calling it yi. This one, you can kind of see based on this f and g function, where is that height going to be? So if we call this distance xi that we're going out here, we know this top function would be f of xi. This bottom location would be g of xi. But what's right there in the middle, right in the middle of that rectangle? Well, one way to do it is just say take an average, right? If I add these and divide by 2, then I'm going to get that value in the middle. So this is, I'm just going to put plus g, and this is, if you want to think about it, of this xi term over 2. So that's what we're going to get right there, is that f plus g function, but divided by 2 to get the average right there in the middle. The area is going to be, right, the length times the width for this rectangle. So in this case, or if you want to think of the height, so how high is this rectangle? Well, it's this top minus the bottom, right? So f minus g is the height. So I get f minus g in there for my height. And again, these are of this particular xi. And then times the width. And the width is just this small little change in x. So we'll put times either a delta x, or we're thinking of using these integrals dx. And actually I might change that back to the delta x real quick. So I'll use delta x till we take the limit, and then we'll put in the dx. What are the moments? So the moments about the y-axis. Okay, so this is from the y-axis over, right, the mass times the distance. And again, this distance, we're just going to use the xi for that one. And then the area is going to act as our mass. So we get this area times just that particular xi, right? So xi times f minus g, evaluated at that xi, and then times this delta x as part of the area. So that is the moment of that particular rectangle. From the x-axis, right? So we're coming from the x-axis up, this mass times distance. And for this one, we're just going to take this y value, right? This f plus g over 2 times my area. So we're going to get, and I'm going to put that up here a little bit higher than the last one. So we're going to get this f plus g over 2, and then times this f minus g times delta x. So f minus g times my delta x. All right, and this should make sense in terms of what we've been doing, right? So we got this distance times this mass, and for mass we're using just area for those guys. Now what you'll see a lot of times in the textbooks is they'll go ahead and multiply this out. So if you multiply it out, we'll go ahead and factor out the 1/2. So I get a half, and then f plus g times f minus g. Hopefully you recognize that. That is going to be just a difference of squares. So f squared minus g squared, and then the x. All right. So a lot of times this is what you'll see in the textbook. All right. So whether you choose to memorize this 1/2 f squared minus g squared, or whether you choose to do the more geometric idea of this height f plus g over 2 times its area f minus g delta x, that's kind of up to you. But this is where that formula comes from. So if you see the f squared minus g squared and you're just wondering where in the world did that come from, it is just that same idea of mass times distance, but the mass being this area f minus g delta x, the distance being this f plus g over 2, and then they just simplify that algebraically. So let's go ahead and do some totals. So like a lot of other stuff in Calc 2, we are thinking of this as a whole bunch of rectangles over this area. So we're going to add these up now, take a limit as these get skinnier and skinnier, which will give us some integrals. So we add up f minus g delta x, right? This is just going to be the integral of f minus g, and instead of delta x, we'll go ahead and put in dx right there. And let's say we're going on the interval a to b. These are all going to be bounded. So we'll just put in beginning a and end point b on those guys. So up in this picture, this coordinate right here, that would have that a, this one right here, that would be where we end at our b for those guys. The my, let's go ahead and add up that my. So my is going to be this integral from a to b, same as before, of, and we can think of adding up all these xi. These are just going to be your x values times f minus g, and then again that delta x is now going to be a dx. And then the last one, again, whether or not, I'm not going to write both down, but whichever one you want to do, this is going to be integral from a to b of 1/2 times that f squared minus g squared times dx. All right, so there's that guy. And again, if you like the top formula better, you can go ahead and put that in. But this one, either one, you can actually pull that 1/2 out and have just f squared minus g squared, or f plus g times f minus g inside that integral. The centroid's going to be the same deal. So this is my area or my mass, whichever way you want to think of it. So you could say either m or area for that guy. This is going to be my my on this one. So this is my m, and this is my moment about the x-axis, my mx. We're going to divide just like before, so I'm not going to write integral over integral, but essentially that's what you're going to do, is you're going to take that moment about the y-axis divided by the mass, or the area in this case, and the moment about the x-axis divided by its mass, or again, we're kind of thinking of that as area for this one. So that's the idea behind these guys. We're going to do quick example to show you what these are, but it's basically just applying these different formulas with your functions on these guys. But so the main idea is just realizing where these formulas come from. We already know about area, but these are the moment formulas that you're going to need, and it's just those mass times distances, sometimes simplified out. So we'll just end it there, and then you'll see a couple examples in the next video.